Feature engineering, generation, reduction, and selection. What are materials features? Features can be named also descriptors and properties, and are these things that connect the data, the raw data, with a machine learning model. Some of the features, or even the majority in some projects, they are on the data sets, but others not. Okay, not all data in the data set is a feature. It's up to you to generate or select the features. So basically, features, they are independent variables that are used as an input for the model to predict an intended output. What is the goal of using features? The goal is to turn your scientific objects into machine-readable columns. For example, you can have crystals, and then you have the coordination, the symmetry, the elements, and you have to transform these into columns that the machine learning algorithms can read. The molecules, fragments, fingerprints, topology, also transform into columns. Particles, size, morphology, surface descriptors. Simulations, you have your computed fields, your spectra, or the energies, and then you have to have these numerical things. Actually, if you use deep learning, you can actually avoid this step. But for that, you need, for example, the detailed positions, for example. Okay, and most of the times you don't have. If you had the detailed positions, you could just run some software to obtain the prediction. Most of the time, the problem is that you have the composition and not really the detailed positions. So most of the times you need machine learning, and you cannot avoid this step. Sometimes you have the structure. You could, in principle, use deep learning, and you can still always use deep learning. But you have numerical features such as, for example, the conditions. Okay, so in a way, you will, in material science and materials engineering and other types, and in chemistry, biology, and other types of engineering, you will always have features. Okay, why are features important? Because machine learning is not magic. What it does is pattern recognition on the features that you provide. Bad features, they can hide the main signals, okay? But good features, they can provide physics and chemistry insights, and this is what we want. What types of materials features are used? You can use experimental, known materials properties that you can measure, like the composition, the morphology, the size, or the surface charge, and many others. Or you can go, for example, for materials informatics. One example is, for example, matminer, which transforms the composition into properties. Or better yet, the structure into properties. But we all, as we told, if we have, sometimes we don't have the perfect structure. Okay, sometimes we don't have a crystalline material for us to do to use a package like matminer to obtain features, numerical features. Sometimes we just have the composition and some characterization, and we need the features, and matminer can calculate these features from the composition itself. Computational simulations. Here is where you integrate machine learning with all these types of simulations. Density functional theory calculations for lower sizes, okay, for bonds, when you know the bonds, when you really know the structure. Quantum chemistry. Force field methods like molecular dynamics, where you can obtain for larger time scales and larger time scales, and for larger system scales, you can obtain many properties. Then, if the system is too large, you cannot do so many experiments. It's too large. You cannot do so many experiments with molecular dynamics or density functional theory, and you can use Monte Carlo simulations. Or if you're dealing with materials uh, under realistic shapes that are used in the real world, you can use simulations with finite element methods and obtain properties with, for example, COMSOL or SolidWorks, Abacus, and many other softwares. Okay. Materials informatics, descriptors that are available in Python. If it's pure materials, you have matminer, which we explained in the last slide. If it's chemicals of any kind, you can use, for example, cheminformatics. Okay, there are materials that have an inorganic part where you use matminer, and uh, a different type of chemical part which can be organic where you can use RDKit. Or, for example, a material interacting with an organic part. And then in the same model you use matminer for the material and RDKit for the organic part, for example. Specific for organic moieties of the materials or organic compounds, you have Mordred, okay, also very nice. And if you need just elemental data, you use, for example, Mendeleev. And so you have several hypotheses, and there are more hypotheses for the materials, but I find matminer to be the one that is easier to use. How important are the features? So, in my experience, the features and the selection of the features can be as important as the algorithm itself. Even a strong algorithm cannot compensate for weak inputs, okay? You can go for neural networks, expend a lot of computational power, but in the end, it's not better than having the right features, okay? It's better to have the right features and use some lower level in terms of computational power algorithm than having uh, uh, expending a lot of computational power doing very large neural networks and not having the right feature, okay? Why feature selection? For example, let's take one alloy where you have one composition, and this will be, for example, an iron alloy, iron-based alloy, okay, a steel, for example. And with matminer, you can have 22 elemental properties: atomic number, electronegativity, covalent radius, melting temperature, valence electrons, ground state volume, and etc. And for each of them, you can compute, for example, 6 statistics. For the whole formula, you can have the minimum, the maximum, the range, the mean, the standard deviation of the mean that you compute, or the mode, and for example, so 6 statistics for many elemental properties. And the more information you have about this alloy, the more you can calculate in terms of properties. This will give something like 132 features, in some cases even more. These features are weighted, by the way, by stoichiometry, okay? Which means that if you have more iron than carbon, for example, in the material, the property, the atomic number, electronegativity of the iron will have an higher weight than for the carbon, okay, in the final value. And that's it. So this is why we need feature selection. Let's see this realistic scenario where we have 132 features, generator for only one chemical formula with matminer, and this is the database that it uses, the MacPy preset. And let's take, for example, from these articles, a benchmark of a dataset, benchmark dataset of steel alloys, 312. So we will have 2.4 alloys per feature before we even add any other type of descriptor, such as, for example, a structure descriptor, or even other types, or using another package. Okay, so it's very easy to, for alloys, 312, if we start using other packages, 12 as many features as examples in the dataset of steel alloys. Why is this a problem? Because too many features and few examples, they mean, for example, noise, irrelevant features obscure the signal, multicollinearity, similar descriptors can confuse the interpretation and degrade the results of the model actually. Overfitting, too many inputs for too few materials. Costs, slower training and harder explanations. And interpretation, they are harder to explain. In the end, the model will be harder to explain. So the goal is to keep the descriptors that carry useful information for a particular model and its output variable. Target, okay. We want to find this sweet spot right here. If we have too little features, for example, 2-3 features, the model will underfit and we have too little information. If we have too many features, we have overfitting and fitting noise, not physics. What are too many features? In my experience, when you have more than 20% of features than examples, for example, in 300 examples, if you have 60 features, we'll start having noise and not physics. Even 30, for 300, probably 20 or less features will be okay. Okay, but it depends on each case and depends on the conditions, depends on the data set and the features that you are using. But more than 60, it would not be okay. It would be you will start fitting noise and not physics. What is the difference between feature reduction and selection? So after you generate the features, you can go two roads. Feature reduction and feature selection. You can actually perform reduction and then selection. Reduction, it builds new axes, okay, new properties, let's say, out of the combination of every original feature. New columns combining the previous individual columns. It compresses hard the dataset and keeps most of the variance. The problem is that the new axes they carry no units and no physical meaning. Okay, so they cannot be verified in the lab with physical dimensionality reduction usually. With feature selection, usually it keeps a subset of the original features, okay, untouched. If you have 132 features, you can find a way of using selection methods and arrive at 10 features, let's say. It usually compresses less, but you can name these features and give to an experimentalist for him to measure in the lab and validate. So, feature selection is the best when the goal is understanding and not only prediction. For example, I would say that the more you go to science and trying to understand, the more feature selection is important. If 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 you want dimensionality reduction, just predict, you can use dimensionality reduction without a problem. Okay. So a selected feature is a hypothesis someone can test in the lab, whereas a principal component usually is not. Okay. So here you can test in the lab and principal component from dimensionality reduction, you cannot, usually. What are the main features reduction methods? The main one is principal component analysis. And how does it work? For example, if in your dataset you have two features that correlate very well with one another, let's say, for example, the covalent radius with atomic radius, they have a high Pearson correlation, for example, 0.92. So you can apply principal component and principal component analysis, and this will transform the two properties into only one. The principal component analysis, it calculates the principal components 1 and 2. 1, which is the line stretched along this cloud of values, and the second one, it's the line perpendicular to it. Since PC1 keeps 96% of the variance, explains most of the results, and PC2 only keeps 4%, you can drop it. In this way, you start with two columns and you arrive only at one column. And this, in a true dataset, you can have more extreme reduction with PCA, with principal component analysis. This PC1 is the base, it's the result of some basic trigonometry where you multiply by 0.71 the atomic radius and sum with 0.71 the covalent radius. In the end, you have a mixture of both. PC1 is a mixture of both the atomic radius and the covalent radius, and it is not a quantity that anyone can truly measure. This one, you know what is being multiplied, and it's easier to verify, but in more extreme cases, it's almost impossible to obtain the PC1, for example, in the lab. What are the main feature selection methods? For me, it all starts with the field specialties, because this is the guy, okay, or the girl that applies machine learning and unifies all of this. It provides the domain knowledge, okay, it has the domain knowledge and provides to the model. Even if the model has features, these features probably were calculated with some input from a field specialist that thought that they were important, or he was the one, somebody planned the experiments, social experiments or in the lab, to have those features. Okay, so it all starts with domain knowledge. So they say in material science, they say what should matter physically. Experiments. This is the person that plans the experiments and says what was observed. Model explanations. Even after obtaining, for example, feature importance with machine learning, the specialist does a lot of work of in terms of vision of giving these explanations and seeing if they validate or not. Okay, why are these features important? And he formulates new hypotheses for the model. What should be tested next? Then there are the statistical methods. And what are the main feature selection methods that can be implemented automatically? We have filter methods, wrapper methods, and embedded methods. The filter methods, they ask this question: can a feature pass a certain statistical test before the training? Okay, before you start really building your model. The wrapper method: does the model perform better with a certain subset of features? For example, you have 132 features. Imagine you question yourself, does the model perform better with these 20? And there are methods for this. Embedded method. It is an algorithm that selects the features while it performs learning. So filter, it's good for a fast triage of to reduce the number of features. The wrapper methods finds the best subset, and within a subsetting comprising all combinations of features, and embedded methods allow to apply machine learning algorithm and still have a built-in selection method. In the end, there is no universal winner. The right method depends on the dataset size, the computational budget, and the need for or not for explanation. Filter methods. It's independent of the machine learning algorithm. It's based on scores in statistical tests. For example, if you have a correlation between the output and some of the features, you can drop those features that do not correlate. Okay. One of the good ways to visualize this is with the correlation matrices, because it allows us to perform some conclusions in analysis for the whole data set. Okay. Even if you have two features that correlate very well with one another, near one, you, in order to not obtain worse results from the model, because this can actually hurt the model, you should drop one of them, having only one independent feature. Okay. And here you use your knowledge of what is most important for your application, or more related to the application, since they correlate a lot with one another. Proper methods. This is where you have a machine learning model, usually non-optimized and run in a fast way, okay, with hyperparameters not optimized, and it's trained and validated on a subset of features. And this can be really any model. It can go from linear regression to decision trees, random forests, or neural networks. And these features, they can be, you start with one and you subsequently add another, or you start with all of them and remove one by one from the model. The thing is, it's more computationally expensive. So, my favorite one, it's recursive feature elimination. You start, for example, with 200 features and you test all the features in the first step without taking one out at a time. And if you take the feature that you take out and has the least impact, it means that it's not important, and so you drop it. And then you do this for 199 features, and then 198, until you have you find from 200, if you have a maximum of 200 features, until one, you select the combination that has better performance. Okay. Or you say that you only want, for example, 20 features, and you stop at 20 features. So the least significant feature is the one that degrades less the model when it is not present and is eliminated at each step. Other feature selection methods, the embedded methods. It's when the machine learning algorithms have a built-in feature selection method. This can be, for example, LASSO regression, which is least absolute shrinkage and selection operator. Okay. For example, if you are going to use linear regression and neural networks, this makes a lot of sense. If you are going to use tree-based methods or ensemble methods based on decision trees, such as decision trees, random forests, cat boost, XGBoost, you are better served using the feature importance based on tree-based methods. Okay, and you drop the features that you see that have no impact, and according to your domain knowledge, also doesn't have a lot of meaning. So when to select filter, wrapper, or embedded methods. Let's see. Filter methods. How do they decide? Filter methods, they take a statistic between each feature and the target. The wrapper method, they train a model on subsets and compares the scores. And the embedded method, the learning algorithm decides while it fits and it trains. So for filter method, the cost is very low. The embedded method, it's still low. You only need one fit, one training, and you have the results. And the wrapper method, as you saw, you need to test many combinations of features, so the cost is very high because you need a lot of model fits, a lot of model trainings, for example. Do you need? Does it need a model? Filter, you don't need a model. Here, yes, the embedded method is in the model, and here you need the model as a black box. So, which means still not optimized hyperparameters. Typical tools. Here will be correlation, multiple information, variance thresholds, wrapper methods, forward selection or recursive feature elimination, and embedded methods, the LASSO, the CISO, or tree importances. What watch out? Filter methods, they ignore interaction between the features, input features themselves. The wrapper methods, if you don't apply cross-validation, it gives very optimistic scores. So every time in machine learning you are evaluating a score or making an option, you should do it based on cross-validation. Embedded methods, the shortlist is tied to that only one algorithm. You use the lasso regression, for example, but this only means that is important for lasso, doesn't mean that is important for all the other algorithms. But still, it can be, in my opinion, I tend to, when you have a lot of features, I tend to use, for example, first lasso to reduce and then do some recursive feature elimination. If I have hundreds of features, I reduce with lasso to 100 and then with recursive feature elimination to the optimal number. If I see that ensemble methods based on tree regression, on trees, such as random forests, XGBoost, CatBoost, etc., are important, I do they perform well, I do tree importance to 100 features and then recursive feature elimination. So in practice, you filter to get the count down of the to go from 200 to 100. Use embedded methods to rank the features from 1 to 10, for example, and wrapper methods if the budget allows, because they really allow to see every combination of features. 3 ways to fool yourself. 3 ways that you can have good results without the results being actually good. Doing feature selection on all the data and only then cross-validating. So the model has already seen the test fold, the part of the dataset that you are going to use for the test, and the reported score is very optimistic and the result will not replicate for new examples. Splitting the data at random, this is the problem, especially for chemistry and materials, because you can have, if you do a random splitting, you can have near identical compositions on the training, the validation, and the test set, and the results will be better than they should. So you should do the split group by chemical family, so the test set is generally unseen chemistry if you are designing new chemistry, because you can just optimizing conditions, for example. So there is also not a standard way to do this right. You have to there is stratified division of the data sets, but it might not be good enough for your specific case. So sometimes you need to define a certain function to define the data well for your case. Reading feature importances as physics. We can interpret feature importances, we do that, okay? But importances, they are specific to one fitted model and a lot can change. For example, more diverse data or different features, they can tell a different story, okay? So, just because a feature is more important, it's not the end of it. You should take the physical meaning with a grain of salt. The final message from feature engineering is that hundreds or even thousands of features are possible to obtain for each material, but only a selected few are important for your model. Thank you very much, and let's go to the next step in machine learning on the next video.